Okay, so we've done completing the square. So what we're going to do is rather than completing the square with specific numbers in a problem, we're going to do a generic completing the square formula. So that's what it says right here. There's a formula that you can use for any quadratic equation. So we're going to start by having a generic quadratic equation like this, and then we're going to go through all of the steps of completing the square. All right, so what it means to actually solve one of these equations is that you would have this set equal to 0. So we're going to work with like this piece right here, because really what we're trying to find are the x-intercepts, and you find those by setting the equation equal to 0. So we're going to work with this, and we're going to do all the completing the square steps. So something like part B up at the top of the page here. If you have something in front of the x squared, the first step is to divide through by that number. So we're going to start there. So we are going to divide everything through by a. And since it's just generic, we're going to have a whole bunch of letters, but just kind of bear with me here. So the x squared will just be an x squared now because the a's will cancel, plus, and then in front of the x we'll have b divided by a, whatever that is, and then we'll have a c divided by a for our constant. All right, so that's step one. Next step is that we're assuming that whatever constant is right here isn't the constant that we need, so we can move it over. So we're going to subtract this. This will cancel just like it does when we're working with actual numbers, and we will have x squared plus b over a times x equals negative c over a. Okay, so now at this point we're like right here. We've moved this term over, so now we do this step. We do the completing the square step where we start with this middle number, cut it in half, and then square it. So again, since we're working generically, it's going to be a little bit strange. So we're going to take b over a. Remember when we were dealing with fractions, it's the same to just multiply by 1/2 instead of dividing by 2. So this becomes b over 2a, and then what I'm going to do is square it. So when I square b, I just get b squared. When I square 2a, I get 4a squared, because remember you're actually squaring the 2 and squaring the a. So the next step is to take that term and add it to both sides. Okay, and then we can complete the square on this. X plus, remember the number that goes in here is half of this, which would be this expression over here. Equals, all right, and then we can clean this up a little bit by getting a common denominator. So this is a little bit strange, but a and 4a squared, we can get them to have a common denominator just by multiplying in something right here. So this has an a and this has an a. What this one has that this does not is a 4a. So I can multiply in 4a over 4a. Okay, so here I've got this common denominator of 4a squared. And then here to me it makes more sense to put the positive one first. So I'm going to put the b squared and then minus, this is 4 times a times c. Okay, so I'm getting super close. I'm going to move up here now. So this is kind of side work, you can ignore that. So next step is to square root both sides like this. Okay, so when I square root, remember I'm just left with the x plus b over 2a at this point, equals, and then when I square root this, remember you always have plus or minus when you square root. Under the square root I have b squared minus 4ac over, and we can take the square root of 4a squared. The square root of 4 is 2, and the square root of a squared is a. So I'm just about done. I am one step from being done with this formula. I subtract this. This will cancel, and I am left with x equals, notice these have the same denominator, so I can write negative b plus or minus, and then all this over 2a. Okay, so this, I am really hoping that this looks familiar to you guys, because if it doesn't, then all of a sudden we get to the end and you're like, okay, cool, that's just some ridiculous formula. This is known as the quadratic formula. You should have seen it in Algebra 1. If you took Algebra 2, you probably saw it there as well, so I'm hoping this looks familiar. I don't know if you would have seen the actual proof behind it before. So there it is. So we're going to write down the actual formula right here, just to have it nice and big in front of us so we can use it for these problems. So we have x equals negative b plus or minus the square root of b squared minus 4ac and then all over 2a. So again, that actually comes from completing the square, which we just did in the previous section. So, fun fact, when I was doing the quadratic formula in high school, we actually learned it to the tune of the Notre Dame fight song. Not that I am a Notre Dame fan, but every time I hear the song, I just think of the quadratic formula. So, this is a lot more embarrassing actually than just doing it in front of the entire class, because it's 6:40 at night and I'm alone in my classroom recording this video, but I am actually going to sing the song the same as I would if I were singing it in class for you guys. So I have a little YouTube Notre Dame fight song. Don't mind me, just going to sing it through a couple times, and hopefully this will stick in your head next time you see Notre Dame play. Okay, here we go. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I think that's probably enough of that. So you're welcome. And let's go through and use this formula and do some of these examples here. So we've got 4 examples. We're just going to get some good practice using the quadratic formula. So basically what we need to do is make sure that we are in standard form, meaning everything is on one side. So this one, we need to move the 33 over. So minus 33 equals 0. So again, you cannot use the formula until you have 0 on one side. So then here a would just be 1. So there's a 1 technically in front of the x squared. B would be a negative 8, that's what's in front of the x, and then c would be a negative 33. So we're just plugging those 3 values into this formula up here. So we've got x equals negative b, so like a negative negative 8, which comes out to be a positive 8, plus or minus square root of b squared, minus 4 times a, which is 1, times c, which is negative 33. And then all over 2a, so 2 times 1 is just 2. So all of this under the square root, you could just plug that into the calculator. Make sure you have parentheses here. So like parentheses negative 8 squared minus 4 times 1 times negative 33. So that's what's under the square root. So that is the square root of 196. All over 2, and then I don't know if you remember the square root of 196. I don't know if you had to memorize it, but it actually does come out evenly. It's 14. Okay, so let's clean this up. So 8 plus 14 is 22. 22 divided by 2 is 11. 8 minus 14 is negative 6. Divided by 2 is negative 3. So those are your 2 values. Remember, as always, I encourage you to store these in the calculator and then plug into the original equation to make sure that they actually are the answers. It would be a really good help on mastery checks and tests. Okay, next one. This one's in standard form. So to plug in to my formula, a is just 1. There's nothing in front of the x squared. B would be negative 34, and c is a lovely 289. So those 3 values are going into my formula. So x equals negative b would be a positive 34, plus or minus square root of negative 34 squared minus 4 times a times c, and then all of that over 2a. So 2 times 1 again is 2. So we can plug, I'm just going to plug what's under the square root into my calculator. So negative 34 in parentheses squared minus 4 times 1 times 289. Okay, so that actually comes out to be 0 if you plug that in. And I'll show you. See, I just plugged all this in, and it turned out to be exactly 0. So if we're looking at this, the square root of 0 is 0. So I have 34 plus or minus 0. Well, whether you add or subtract 0, you're going to get the same thing. Like 34 plus 0 is 34. 34 minus 0 is 34. So really all I need to do is take the 34 and divide it by 2, and that gives me 17. Again, do a quick calculator check. Make sure you got it right. Okay, example 3. We've got a is 1. There's a 1 in front of the x squared. There's a negative 6 in front of the b. I'm sorry, in front of the x, and there is a 2 as a free floating constant. So we can plug those into our formula. So x equals negative b, negative negative 6, b squared minus 4 A, C. All of that over 2a, so 2 times 1 is 2. Okay, I'm going to plug what's under the square root into my calculator. So negative 6 squared, oops. Oh my gosh. Squared minus 4 times 1 times 2. So I get a 28. So there's a 28 under my square root. Okay, so I'm trying to give you a taste of like some different scenarios here. This scenario, you've got 28 under the square root. It's not a perfect square, so we can do really the best we can with it, and that's just to simplify it. So 6 plus or minus, so root 28. 28 splits off into 4 times 7. 4 is a perfect square, 7 is not. So the square root of 4 is 2, and you can bring that out, and then there would be a 7 left underneath. Okay, then since this is all over 2, we can divide both of these terms by 2. So 6 divided by 2 is 3, plus or minus, and then 2 root 7 divided by 2. The 2's would cancel, and I would just have the root 7. So as ugly as this answer is, you just want to leave it like that. Don't plug it into your calculator and get a decimal. Okay, last one. There is a 3 in front of the x squared. There's a 5 in front of the x, and then a free-floating 4, oops, would be your constant. So for our last one here, plug these all into the quadratic formula. So x equals negative b, be negative 5, plus or minus square root of b squared, minus 4 times a times c. And that is all over 2a, so 2 times 3 is 6. Okay, so one last time, plug this stuff into your calculator. So 5 squared minus 4 times 3 times 4. So I get a negative 23 under the square root. Okay, so you can see that this is yet another example. We haven't seen a negative under the square root yet. Remember from section 4.4, you can take an I, the imaginary number I. And the 23 doesn't simplify any further than that. If it did, you could simplify it the same way we simplified this one. But it's really just the 23 altogether that's left under the root and all over 6. So again, as ugly as that answer is, that's really all we can do to simplify it. All right, that's it. Okay, so in the previous video, we saw 4 different examples, and I'm going to take you back to what those examples were. We saw one example that had 2 answers, but they were nice, normal, neat answers. We saw an example that had just 1 answer. This one had 2 answers, but they were weird, irrational answers with square roots. And then this one had imaginary numbers, so overall these were complex answers. Anything involving I makes it overall a complex answer. So we have 4 different categories that we could end up with, and there's actually a way to find out before you even do the quadratic formula what type of roots you're dealing with and how many you're going to have. Okay, so value of the discriminant. We have 4 different scenarios here, and it's all based on the discriminant. So let me write the categories that we had here. We had 2 rational roots. That was the first example that we saw in the previous video. We had 1 rational root. We had 2 irrational roots. And then finally we had 2 complex roots. Okay, so I'm going to flip back to that previous video again and show you how we could have known. So here's the difference between all 4 of these answers here. It's not this, it's not this, it's whatever's under the square roots. So this, we had a 196 under the square root. 196 is a perfect square. The fact that this was a perfect square is what made this a nice, neat, pretty number, which made these nice, neat, pretty answers. So in order to end up with 2 rational answers, you have to have a perfect square under the square root, and it has to be positive. Okay, so if our discriminant is positive and it's a perfect square, we will come up with these nice, neat answers like we did in example number 1. Okay, let's flip back to the one where we got 1. Well, here we only got 1 answer because there was a 0 under the square root. Okay, so a 0 under the square root is what we would end up with here. Okay, and I should actually, I'm sorry, we should trade these because this picture won't make sense. Let's make this one the 2 irrational, and we'll make this one the 1 rational. Sorry about that. I wasn't really paying attention to what I had over here. So one rational would be if your discriminant is equal to 0, because adding 0 and subtracting 0 doesn't provide you with two unique solutions the way this does. Okay, the irrational. The irrational, we had an example of 28 under the square root. It's a positive number, so we get real answers, but it's not a perfect square. So because this isn't a perfect square, this doesn't simplify, and I have kind of icky, irrational answers. Okay, so this is if I have a positive number, but it's not a perfect square. Okay, so that's what I mean when I say non-perfect. It's not a perfect square the way that other example was. And then finally our complex answers. The reason these came out to be complex is because I had a negative under the square root for that last example. So if my discriminant is negative, I am going to come up with two complex answers. Okay, so sample graph. I would have two irrational roots if my graph looks something like this. If I had like a normal parabola went through, I would have two x-intercepts. They might be rational, they might be irrational, I don't know. You could have a different scenario where your graph is upside down. So whether right side up or upside down, this is a sample where you would have two different x-intercepts. Okay? One rational number would be if your graph looks like this, if it just perfectly touches the axis and then bounces off like that. And you could have a similar picture for an upside down parabola. And then two complex would be one of two cases. Either your graph is right side up, but it's completely above the axis, or your graph is upside down, but it's completely below the axis. So this would be a case where you never ever cross through the x-axis, so you wouldn't possibly have any x-intercepts. So that's what we're looking for. We are going to, for each one of these, find the discriminants. And by the way, the discriminant is just that value that's under the square root. So that's our formula. It's just that piece of the quadratic formula that's underneath the square root. Okay, so when we find the value of the discriminant, we'll write it right here so it's in sight. We're going to do that first and then classify which category it would fall into. Okay, so here, the discriminant, b squared minus 4ac, we can fill in the following values. Here b is 8, that's the number in front of the x. A is negative 5, that's the number in front of the x squared, and then c is negative 1, that's the number that's just hanging out by itself. So we could plug this right into the calculator. You've got 8 squared minus 4 times negative 5 times negative 1. To enter, we come up with 44. Okay, so what we want to do is see which one of these categories 44 falls into. It's positive, yes, but it's not a perfect square, so we fall into this category right here. So based on that, we know we're going to have two irrational answers. So this is part of my answer, but then also stating what type and how many solutions I'm going to have is also part of my answer. Okay, next example. Be careful with this one because it's out of order. B is always the number in front of the x, no matter what order it's in your equation. And then minus 4, a is always in front of the x squared, and then c is always the number hanging out by itself. Okay, so let's plug that into the calculator. Negative 7 squared minus 4 times 15 times negative 4. That comes out to be 289. So again, that's the first part of your answer, is the actual value of the discriminant. It's definitely positive. Is it a perfect square or not? It actually is. 289 comes out even. The square root of that is 17. So it is a perfect square, which means I am going to have two rational numbers. Okay, so I think, yes, that's it. You could also have one of these two scenarios, so just keep this chart with you. The last thing I have here is all of the methods that we have used so far for solving quadratic equations. So this is the last one that we learned. Quadratic formula could always be used no matter what, whether it's factorable, whether they're complex answers, whatever.